Hello, Namaskar. First part we already done that view. We already viewed. If you not view, I will share a link. Okay, YouTube link. In first part, I explain. I just tell you that the solution of first two questions. Okay, first two questions we discussed. Now here in this video, we will learn. We will understand the solution for question number 3 and 4. The both question are uh, optional each other. Okay. So, but we just consider how we go to give an answer to questions. Okay. So let's start. So question 3, define phase sequence, balance load, unbalanced load. This is the three terms we have to define. Okay. And it is a question for 3 marks. Okay. So now how we going to answer it? So here's definition. The every students their mind are different. Okay, they thought differently. They give the answer on the basis of element. Okay, in a like this in a delta or star, there are load are balanced. The load are equal. These are also correct. But the actual demand, actual concept, what tells? You have to write. Okay, you have to answer. Okay, so definition for phase sequence: the sequential order in which the voltage waveforms or current of a three-phase system reach their peak positive value. Okay, okay. So number of multiple phases are there, and among of these phases, okay, phases, which phase is firstly reach at its peak value. It's considered as a first phase, okay, and so on. Subsequently, we consider second, third, okay. So this is a example here are given, okay. So there's our ABC, ACB, negative phase sequence. Example are there, nothing issue. Next, balance load, a three-phase load where the impedance and power factor are identical in magnitude and angle for each of the three phases. Okay, the balance load. There are three phases normally in our electrical system, and each and every phase have same balanced same value of impedance. Impedance means Z. Okay, it is the complex term. Do you know that R plus J X? Okay, next, unbalanced load. Unbalanced load is simple as load where impedances or power factors differ between phases, means loads are unequal, meaning is load unequal is considered as the unbalanced load. Simple, very simple. Okay, these are terms. Now next question number 3b, derive EMF equation of single phase transformer. This is a question for 6 marks. It is a derivation, simple derivation. Okay. So according for this derivation, we have to start with the first conceptual thing is Faraday's law. What tells Faraday's law? Faraday's law tells when an alternating current flows in the primary coil, it produces a sinusoidally varying magnetic flux. Okay, flux here considered as a phi. Okay, in the core given by phi is equal to phi m into sine omega t. Okay, where phi m is the maximum flux and omega is angular frequency, which is considered as the 2 pi f. Okay, angular frequency, radian per second. It's a unit and it's represented as 2 pi f. So instantaneous EMF is, okay, the Faraday's law states that EMF E is a rate of fluxes of flux linkage is equal to minus n d phi upon dt minus, it's a for we consider Lenz's law, okay, as a nature of EMF generate, it's a opposing nature, okay, to it's a causes of production, okay, causes of produce, hmm, means source, okay. सो जो काय सोर्स आहे त्याला विरुद्ध करण्याचं काम तो ईएमएफ करतो. सो इट इज कन्सिडर्ड ॲज अ नेगेटिव्ह. ओके, अप्लाइंग टू प्रायमरी for primary winding, n1 is the number of turns at a primary winding. Okay, just multiply it. Okay, so formula become like this and take a differentiation. Okay, complete a differentiation. This is a phi is a trigonometric function. It's a represent in a sine omega t. करेक्ट आहे. तर ह्या पद्धतीने आपण डिफरन्शिएशन घेतलं तर आपल्याला मिळतं cos omega t. Okay, you get that, you get a cos omega t and you can replace this cos omega t by, okay, sine of omega t minus pi by 2. Okay, and it's a become negative term. Okay, so because of this negative get cancelled and become a positive, and by this way we get that whatever you generate the EMF it is a normally lagging. Okay, so the EMF next term is RMS value. It's considered as the average value. Okay, it's average or not average, we can consider as a normally maximum value because here is a sign of phi m. So to find a RMS, okay, RMS is normally average value for the alternating quantity. Okay, it is a fixed quantity. You can take a value. Okay, while there is the alternating value. Okay, you have to constant value. You taking RMS value. RMS value means is equal to that peak value upon root of 2. Okay, so A1 it is 1 for primary winding voltage peak value is equal to, just take this term only, N1 pi m and omega. Okay, just substitute that omega replaced by 2 pi m. Okay, you get the value like this. RMS is equal to E1 is equal to E1m upon root 2. You get the calculation that like this way, and phi you get that is equal to root of 2 pi f and 1 pi m. Okay, the value of root 2 into pi is equal to nearly equal to 4.44. Okay, so next that we get the AMF value. E1 is equal to 4.44 f and 1 pi m. Okay, simple. You can differently solve this. Okay, different way. We get the graphical way. Okay, next question. 3 identical impedance each of 6 plus j8 are connected in star across 3 phase 400 volt 50 hertz supply. Determine phase current, line current, and line phase voltage. Fourth one, three phase active, reactive and apparent power. This question for 8 marks. Very simple question. Okay, but you are clear about the concept. Okay, just you have to clear about the concept. Here it's giving network as a star connected. Okay, so this is very important, and it is balance, very simple, then it's become very simple. So next that how you solve it. The step first, you are going to calculate impedance, magnitude and angle. Okay, you value get the impedance of 10 ohm. Okay, here on the screen you get the value. Okay, then phi angle of 53.13 degree means power factor of 0.6. Each term is assigned 1 mark. Okay, next you have to calculate a phase voltage. You get a phase voltage of 230.94 volt. Okay, so line voltage remain 400 volt, no issue. Next, the phase current Vp upon Zp is equal to, you get that, just 23.09 ampere. Okay, line current and line phase current is same in star network. Then next very simple thing, you're going to calculate active power. The active power formula is like this: root 3 VL into IL cos phi is equal to root 3. The calculation you get that 9600 watt, 9.6 kilowatt. Then reactive power, just we have to replace the cos phi with sin phi. You get the term as a 12,800 watt. Okay. Next, apparent power, S is equal to root 3 VL into IL. You get 16,000 volt ampere, 16 kVA. Okay, very simple questions. Then next, state the relation between phase voltage and line voltage. Okay, this is OR. Okay, question number 3 is a OR question. Question number 4. Okay, then you have to just set the relation: phase voltage, line voltage, phase current, line current. Okay, in case of balance, here is very important. Last term is very important. Delta. Okay, first third question is assigned, it is allocated for only star, and fourth question is allocated for delta. There is no any kind of we can say a speciality of any concept. They are actual optional to each other. Okay, ते एकमेकांना कसे आहेत तर ऑप्शनल आहेत, बरोबर. सो राईट डाऊन द एक्सप्रेशन, थ्री फेज अँड ऍक्टिव्ह पॉवर. सो त्याचं कशा पद्धतीने असतं रिलेशन, की जर आपण डायग्राम ड्रॉ केली डेल्टा कनेक्शन मध्ये, तर डेल्टा मध्ये जशा पद्धतीने लाईन व्होल्टेज आहे तशा पद्धतीने ते फेज मध्ये, फेज पॉइंट्स मध्ये अकर होतं. ओके, सो यू गेट दॅट VL is equal to VPH and phase, it is just 1 mark. प्रत्येक रिलेशन ला 1 मार्क आहेत. Okay, IL is equal to root 3 VP IPH. So we have to multiply only root 3 with a phase current. मुलं काय करतात परीक्षेत, मुलं उलट लिहितात. ओके, IPH is equal to root 3 of IL किंवा इतर root 3 घालतात. ओके, सो अशा गोष्टी घडतात. सो हे होऊ नये. ओके, त्यासाठी या गोष्टी क्लिअर झाल्या गरजेच्या आहेत. आणि पेपर जरी केलं तरी आपण सगळं सोल्युशन प्रॉपर करू शकतो. ओके, you just have to solve the question paper, you get the proper idea about the subject and you will pass. Now the expression for three phase active power, this is simple, this is common, there is no difference between star and delta, this is common. Okay, P is equal to 3 VL into IL cos phi. Okay, and phase value power is the 3 into, just here we have to remove root term. Okay, 3 into VPH IPH into cos phi. Okay, You have to term define here. You get 3 marks. Next, differentiate core type, shell type, transformers. Okay, so there are 6 differentiation. Okay, any point 6 point. Okay, 6 point, each point carry 1 mark. Very simple. First point, core and winding arrangement. How you arrange? In core, the core surrounds the windings. Okay, windings on limb. Correct. Hmm? Then in shell, core surrounds the winding. Okay, windings on the central limb. Just central limbs. Number of limbs, core type has a 2 limbs. Okay, limbs means we consider that vertical component of core. Okay, this is a limb. Hmm? While shell type has a 3 limbs. Correct. Winding type, core type is a concentric cylindrical windings. Shell type, sandwich interleaved winding. Fourth one, magnetic flux path. Magnetic flux path, core type has a single path, flux path. Okay, and in a that of shell type there are 2 paths. Flux are gets filtered in yolk. Okay, then maintenance and cooling. Core type offers better cooling, easier. Okay, and the shell type poor cooling, harder maintenance. Okay, mechanical strength and application. Shell type has a higher mechanical strength. Okay, brassing आहे, protection आहे. Is good for industrial low voltage, while core type has a lower strength, better high voltage power application. Okay, so these are differentiation terms. Next, last question of this video. There is a 25 kVA 50 Hz single phase transformer has a iron and full load copper loss of 350 watts and 400 watts respectively. Calculate efficiency at 50 or 50% full load at unity power factor, and this is called for marks. Okay, 75% of full load at 0.8 lagging power factor. Okay, so how you solve it? So the first step, basic efficiency formula, that output power upon input power. Okay, input power means it's a sum of output power plus losses. Just you have yes is a full load capacity of transformer. Okay, it is rating. It's a actual rating we consider as a full load capacity. It's 25 kVA and its loss is 350 watt. Iron loss, copper loss is 400 watt. Okay, it's variable loss and it is a constant loss. Now your case have first case for 50% loading. Okay, and power factor is 1. Okay, unit power factor halfly loaded. So how you calculate it? Just calculate first of all output power. That output power is formula 0.5 into 25 into 1 means the Vi into cos 5 is active power and it's a multiple with the factor of x. It's a halfly loaded. So we get output power of 10,500 watt. Copper loss. Copper loss of we can calculate like loading square into watt. Okay, 0.5 square into 400 watt. Then losses total loss that is considered in case. Okay, in that case copper loss is different. Okay, it is variable, it's not a fixed loss. Okay, so Pi plus copper loss 350 watt plus 100 watt, you get 450 watt, and you calculate simple formula P out upon P out plus P losses, that is 12,500 upon 12,000 plus 450, you get a value of efficiency 96.5%. 53%. Okay, this is the first sub question answer. Okay, it is having for 4 bar. Next, X is the loading of 75% load. Okay, so for this 75% power factor is 0.8. Output power for this case, okay, X multiple with the total capacity and power factor. So you get that 15,000 watt output power. Next, copper loss is different. So multiple factor square into total copper loss. Okay, so 400 is total copper loss. So multiple with the square of X factor loading factor. You get the copper loss of 225 watt. The total losses is iron loss plus copper loss. You get 575 watt. So efficiency is that 15,000 upon 15,000 plus 575 the total loss. You get efficiency of 96.30, 96.30, which is for 4 marks. Okay, so here we stop. If you have any kind of doubt, okay, any kind of problem, any kind of questions, you ask me on this number. You can directly call me. Okay, you can the contact number is available. Okay, I cannot be enabled the comment section. Okay, so lot of students their comments are different. Okay, no, I am not going to contact to them. There is a, so you, if you want, you can call me on this number. Okay, so thank you. I will share next video very soon. Good day.